Hello friends, welcome back to our discussion or simulation on pendulum system in Simulink. We'll continue where we left off in the previous lecture. Now let us go ahead with a different methodology to obtain the angular position and angular velocity using state space linear model. Notice I have written here linear now. So here the model is considered linear which is good approximation for small angles only. So let us rewrite equation number 14. So x1 dot, the state space form here it is written as x1 dot equals to x2 and x2 dot equals to, the linear form will be 1 by ml square into t minus g by l into x1. Notice we have x1 here, not sine of x1. So what implications it will have in simulation we will get to know. C by ml square into x2. So writing in matrix form, we get x dot x1 dot x2 dot 0 1 minus g by l minus c by ml square, x1 and x2 plus 0 1 by ml square into t. So if you see this carefully, we have x1 dot equals to 0 into x1 plus 1 into x2 plus 0 into t, that is x1 dot equals to x2. x2 dot is minus g by l into x1, this is minus g by l into x1 minus c by ml square into x2 minus c by ml square into x2 plus 1 by ml square into t, so 1 by ml square into t. So that is x dot, it is written as ax plus bu or b into t, which is the control input, and y is 1 0 x1 and x2. That output I am assuming only the position. Cx plus du, anyhow d is 0. Now let us draw a block diagram for this x well. So here we have only one integrator. Here is, this is x dot which is yielding x. So this is multiplied by x dot equals to ax plus bu or bt in this case. So we will write here a. Now remember, this a is a matrix now. Here we have summing block plus plus, and here we have x dot equals to a into x plus b into u or t. So here the matrix is B and here the input is torque. So this is the block diagram for x dot equal to x plus b into t. Now let us quickly plot this in Simulink. So till here we have done in the previous lecture. Now we have only one integrator. We have initial condition x naught, writing gain k, control I. Now what is A matrix? A matrix is 0 1 0 1 colon minus G by L minus C divided by ml square, m into L square. Now this is a matrix here, so it should not be an element wise multiplication, it has to be matrix into U, because the output of this here it is a vector, and this gain k will be multiplied by an input which is a vector, hence it has to be matrix k into U. Then B matrix, here B is given as 0 1 by ml square. So this can be element wise matrix. Why? Because here the input to this block is a scalar, it's not a vector. So I'll just use the same torque here. One second. Here we need to add the summing block. Now this signal will go here, this one in this way. Now this torque will be here, right? So now here we have a vector. Now again we need to demux the signal so that we can easily plot x1 and x2, which is angular position and angular orientation, velocity. Right clicking and simply dragging. All right, so here we have initial conditions mentioned. This is the A matrix and this is the P. Likewise that we have done here. Now we are ready to run our code. All right. Now we have here figure 1. We go to our model. This is the angular position and this is the angular velocity. All right. Now we again observe here that we get similar response, similar results, irrespective of the methodology used. You can compare these plots. All right. Now let us use same state space block that is inbuilt state space block. So MATLAB provides us this inbuilt state space block. I'll just write state space block. If you double click this, so the equation is already in this format: x dot equal to x plus bu, y equals to cx plus du, and it will ask for the A matrix, B matrix, C, D with the given initial conditions. So initial conditions was x naught. All right, it will not let me finish. We need to enter the matrices here. This is A, this is B, and then we have C matrix as well, 0 1, and D 0. So we have apply. Okay. What we need to do here is again plug in this signal as an input to this block. All right. Let me close these figures. We will just copy this code here. And see if there is any problem. Control S, run the code. Yes, so there is some issue here, error due to multiple causes. Input port dimensions are being set to 1. All right. We'll change this to 0 0. Let us see now. All right, so similarly D also needs to be changed. All right, let me try now. Yeah. Now if you plot this, this is the position and this is the velocity. So there is some issue in velocity here. Let us see what that is. All right. So what we did here was we have written C matrix X 0 1. All right. So let us write that here. So y equals Cx plus du. Anyhow D is 0. So this is Cx. So earlier I had considered Cs 1 and 0. But since x is a vector x1, x2, I had to mention the state space block 1 0 0 0. So for to get the velocity vector, I need to change this C matrix to 1 0 0 1. That is how when this is multiplied with by x1 and x2, so y will be x1 and x2. So this is 2 by 2, this is 2 by 1. It will be 2 by 1. Yeah, 2 rows, 1 column. Hope this is clear. Let me change this to 1. I am saving it. Now rerun the code. All right, I didn't close this. All right. Now this is angular position. Now we have angular velocity. Now again we get a similar response. Let me all right. We did a little bit mistake here. It should be 1 0 0 1 and rest of the things are okay. So now if I run this code, and check this position, angular position and angular velocity. Now we get a similar response over here, angular position and angular velocity. Now let us go ahead with our final methodology, that is transfer function approach. We will get to know what is the limitation for using that approach. Let us proceed using transfer function approach. Now again taking Laplace transform of equation number 13 with 0 initial conditions. So we have s square theta of s equals to 1 by ml square t of s minus g by L theta of s minus c by ml square s into theta of s. Theta of s I can write it as 1 by ml square t of s divided by s square plus c by ml square to s plus g by L. So transfer function can be written as theta of s by t of s 1 by ml square upon s square plus c upon ml square into s plus g by L. So this is the transfer function. Now let us plot angular position and angular velocity using transfer function approach. All right. I will write here transfer function. I will simply write what is actually in numerator coefficients. I will simply write from here. I have written already earlier. Apply, okay. Apply and okay. All right. Let me make it a little bit bigger. All right. Okay. Now this is a transfer function approach. We will put an input again here, which remains same. I am not changing input, hence expecting the similar results. Radians to degrees, and we have scope. All right. I am saving it and I am running the code. So we get the similar angular position response here. How to get angular velocity? By actually doing the differentiation of this signal. So to that, write derivative of this signal, and then finally I am copying it. All right. Control S, double click, and run this model. So now we have velocity as well, which is going to 0. Now we have tried different methodologies. One is by using the MATLAB function and then using this block diagram. You can write here actually by annotations. This is by MATLAB function. And this is by block diagram. This is similarly state space approach, even this one, and this is the transfer function approach. All right. So we have tried 1, 2, 3, 4 and 5 methodologies, and we get similar results. Okay. Now let us do something different. Now let us see and plot with different initial conditions. Let me write here, instead of 0 degrees, I am writing here 200 degrees. So what I am actually doing here, let me go to the figure. All right. So plus 200 degrees means it will, the initial condition will be here. So this will be 180 plus 20 degrees, so 200 degrees. So when you drop it from here, then you expect this to go in this way and then oscillate like this. That means it will, after reaching 200 degrees, or initial condition is 200 degrees, it should go further. The angle should further increase towards 360 degrees and then go back and go forth. Now let us see if the model that we have done is able to predict it rightly or not. I am running this code with the initial condition as 200 degrees, all right, and run. All right. So this is the first model that we have considered a MATLAB function, that is nonlinear model. So it is currently, it is rightly predicting that indeed it is going beyond 200 degrees, and further later on it is settling to around 371, that is 11.2 degrees from there. All right, and the velocity is again going towards 0. Let us see now. Now this is the block diagram. All right, let us first check this. Now this is the as per the block diagram theta. So here we have, it is rightly predicting and settling towards 11.8 degrees, and this was the previous response. And the other approach was a linear model, x dot equals to ax plus bu, and if you see here, it is saying, this graph is saying that somehow it is going back to its 0 degrees and again oscillating back and settling down to 0. So this happened because we removed the nonlinear term sine of angle. So this is a linear equation. This is a linear equation. Linear system. So as I mentioned in the note earlier, that for small angles linear approximation is correct. So linear approximation is only valid upon small angles. Now this 200 degrees is obviously a huge angle. It is, the simulation is not able to rightly predict that it is indeed going further. Then finally state space approach. Here also we observe the same thing. So here again we have a linear model approach which is not able to predict the correct simulation. Then finally transfer function. So what do you think the response will be here? It is still predicting the same thing. The reason, there is no methodology to enter the initial condition over here. So, that is one of the drawbacks of using a transfer function. It is always assumes the initial condition is 0. Now, finally, before I end this discussion on pendulum equation, let us predict one more situation where I have considered different input. So, when t is less than 5 seconds, then torque is ramp input, which you can consider as slope as 1. When t is greater than 5 seconds and t is 0. So, what I mean with this is the torque is actually increasing linearly with time, and at 5 seconds it is 0. So, here slope is 1. I will consider here same, at 5 seconds it is 5 Newton meters, this is 0. So, this is nothing but the input instead of the step input that we did earlier. Now, how to do this in Simulink? We use this switch block and write here threshold limit of 5 seconds. The torque is 0 after 5 seconds. And it is a ramp input for the first 5 seconds. I will write a slope here, start time 0. All right. Okay. Now, instead of this step input, we will try with this switch block of ramp input. So, this 5 indicates time. We have time. All right. And let us see if whether we are getting the similar input that we are expecting or not. We will put scope here. All right, I am saving the model, and let us put the initial condition back to 0 just to check how it is working. All right. So, you can see here, before checking this, let us see the input. Yes. So, now the input is actually increasing linearly with a slope of 1 up to 5 seconds, and then it is 0. Now, see the response of this. We again observe here that it is going, since the torque is going to 0, the angular position, it is coming back to its 0 degree position. You can see here linear variation of this torque up to 5 seconds. Let us see now various models that we have modeled before. This we have already checked. This should be the similar response. Yes. Yes, similar response, and of course, we will get the similar response because the initial condition is 0 and the angle is very small. So, you can test with very different initial conditions by entering different control inputs and test the model. So, by now I think you must be Now, this must have given you some understanding of Simulink model, how to use it for simulating different dynamic systems. In the next week, we will begin simulating of aircraft 6 of equations of motion, both in MATLAB and Simulink. Thank you.